Kelli McCoy is currently a senior systems engineer at NASA Jet Propulsion Laboratory, working to promote the infusion of uncertainty quantification, machine learning, and risk-informed decision-making practices across the systems engineering organization. Before joining JPL, Kelli gained valuable experience at NASA headquarters and Kennedy Space Center. Her research interests include statistical learning theory, digital twin analytics, and probabilistic risk analysis. This morning, she's going to present to us a topic entitled Artificial Intelligence, Machine Learning, and Uncertainty Quantification in Systems Engineering.
So I'm going to talk today a little bit about AI ML, specifically large language models, and uncertainty quantification and how it's applied in systems engineering. I'll start by defining UQ. Probably most of you in the room don't need a definition, but I'm kind of going to broaden that traditional definition a bit. I'm going to talk about how we use UQ in systems engineering to identify risk, but also opportunities, which has proven invaluable at JPL. And then secondly, we'll move on to large language models and machine learning and how we can implement that to make systems engineering more efficient. So just starting with the definition of UQ, I personally see it sitting at the intersection of domain knowledge like engineering, physics, computer science, and math, specifically probability and statistics. And so throughout this presentation, I'll kind of use the definition, come back to the definition of uncertainty quantification, lending itself to the use of probability and statistics. So nothing deterministic here in this process. But it can be any type of simulation, an analytical construct or a numerical construct, can be wrapped around a machine learning algorithm, things of that nature. We use uncertainty quantification here at JPL to capture the inherent variability in systems and models of those systems. So I think both of those concepts are key here. We have found it to be invaluable to improving decision-making, specifically on things like stabilizing our project baselines early, informing requirements, balancing this cost-risk trade we're always making, and revealing cost-saving opportunities that otherwise wouldn't have presented themselves. We're implementing it both across early formulation, where we're understanding the feasibility and trade space of missions, understanding early risk assessments, and then moving on into implementation, where we're actually building this thing, validating and verifying, and even operating these missions. So the way I'm going to structure this is to kind of go through a few examples, both with UQ and with large language models. So this first example is really focused on technical resource estimation and setting requirements for things like mass, power, a lot of the resources that are in demand across a space mission. And I like to think about technical resources in a load and capacity standpoint, or demand and production, if you want to think of it that way. And what is traditionally done here at JPL, and I would venture to say across NASA and maybe DoD as well, you have some kind of load, maybe think about power demand, and you add growth allowances, you add margin, but it's largely a deterministic process, and you set a deterministic requirement. And then, on the opposite side, you're estimating the capacity you need or the production you need in the case of power, for example, and you're setting sort of a minimum production requirement. Again, all deterministic. But this really doesn't lend itself well to understanding risk or understanding need. It's just a blanket factor that we're adding onto our load or capacity. So what we're trying to do with UQ here is start to shift that paradigm and really think of margin and cost as cost and complexity. Every time you're adding margin, you're adding something to your system. So in the case of power, maybe you're adding solar cells to your solar array, for example. But these come with dollars and often complexity. We really want to stop using margin as risk mitigation when we don't understand it and these probabilistic methods associated with UQ can help us understand this risk posture better. So what does this mean? And can we start to do better? So either by looking at one or the other or both sides of this equation, we can start to build probability distributions of our resource. So on the left, maybe you're building a probability distribution of your launch mass, and you want to set a requirement, for example, that you don't exceed your launch vehicle allocation by a certain risk threshold. And that can be all mission risk class dependent. So if I have a very expensive, high dollar or high value science mission, maybe I am more conservative with my risk posture and I'm setting my requirements accordingly. On the right-hand side, I'm just showing a quick example of where you treat both load and capacity as probabilistic or uncertain. And you're really looking at a probability that your load is exceeding your capacity. And in this case, I'm showing a radiation example. So my total ionizing dose, does that exceed my part hardness? And what's the probability of that occurring? And traditionally at JPL, we just put a factor, we call it an RDF factor of 2, and we move forward. But that can, again, be very expensive, and we don't actually understand the risk associated with that factor. What might this look like if we move to an alternate paradigm and start to establish requirements instead of blanketly adding margin? This is just a probability density function of, let's say, end-of-life power. And we want to set a requirement on our power generation. And I just made this up. The system shall generate end-of-life power greater than 10 watts. So you kind of draw your vertical requirement bar here at 10 watts. And the probability that we exceed that is 10%. And maybe that's good for your project. Maybe you need to be more risk averse, or vice versa. So then, you might come in traditionally and estimate, well, I've set my requirement for my capacity. I'm going to build a solar array to meet that capacity. But actually, as I'm constructing this solar array, I think I'm actually going to get a capacity of 12 watts. So that's good. Now my probability that my load is exceeding my capacity is 1%. But again, that additional capacity likely came with cost. And I think we need to start asking ourselves, is that risk reduction worth the cost and complexity? So in actuality, we've treated this current best estimate of capacity as deterministic. But as we saw in the previous chart, you can also think about that capacity probabilistically. So this is the other half of the equation, if you will. And when you align the requirement there with your capacity, you see that the CBE, or the current best estimate of your solar array capacity, is actually the 11th percentile. And you have a lot more capacity at your disposal when you look at it this way. So really you're carrying a lot more complexity, a lot more cost associated with this green area than you ever knew that you would, that you were if you hadn't done this type of analysis. So again, we can look at both sides of this equation, load and capacity, and start to generate probability distributions for both. And the risk region we're worried about, of course, is this red area. And when you start to do it this way, it really allows you to start to move off of this margin posture that you don't really understand in terms of risk and opportunity, and move to a more thoughtful requirement setting and risk analysis posture in your missions. So that's just one example, and my next few examples translate this into practice. So on Europa Clipper, we wanted to understand the probability a given part would exceed an RDF of 2. And the way we define RDF is radiation design factor, is our part hardness divided by our end of mission expected total ionizing dose we will see throughout the mission. The way we did this, the way we constructed this PDF, which might have been top of mind for a lot of you, is how do we even construct these PDFs? We had visited Galileo before, and we understood that Jupiter environment where Europa Clipper is going. We had a lot of data, and we were able to understand through that data set both inter and intra-orbit dose correlations and employ some ARIMA and other time series methods to derive the curve you see here on the right. And so we were able to quickly assess that there was little to no risk of exceeding this RDF of 2 for a single part, which was really good. If we didn't shield that part as much and just stuck to an RDF of 1, the probability we would exceed that in the Europa Clipper tour was about 45%. So, that might sound pretty high for a lot of people. And it was. So we stuck with RDF of 2. And ultimately, that turned out to be really good because a lot of our parts later in testing were shown to be less rad hard than expected. However, there are many parts. This is just one part. And while this is overly simplifying assumption, if you consider all of the parts as independent of one another, the probability one or more exceed RDF of 2 is 0.036%. Again, pretty low risk, but the probability you exceed RDF of 1 is 100%. And given a lot of the late part testing issues we saw, we were glad we had that RDF of 2 in place because we came down closer to this RDF of 1. Another example, using Europa Clipper, again, harsh radiation environment, we wanted to understand the susceptibility of radiation-induced outages and what that might do to our science collection story. So we have a simulation, you see on the right here, kind of stochastically removing pieces of our coverage story. And then we have a graphical statistical representation of our requirements, science requirements, leading up to level 1 requirements, all the way from measurement requirements. You can see there are multiple paths to achieve this level 1 science objective. And so imagine, taking out these chunks of observations and how that might propagate through this graph to yield a probability of achieving these level 1 science objectives. But all of that is dependent on how quickly we might recover from some of these radiation-induced temporary outages, like SEUs, for example. So what we were able to show through this analysis, and this is where UQ can really yield some savings if you do it right. We had planned prior to doing this analysis that we needed an autonomous recovery, which was driving triple redundancy, hot backups, a novel restart software so that we could recover fast wherever we were in our trajectory. And this was about a $40 million solution. And this infrastructure showed that that was not necessary, that we had enough robustness in this graph that we did not need to do that. So that was, again, a success story for implementing UQ. Another success story that ended up saving quite a bit of money for the Europa Clipper mission was employing UQ on planetary protection story. And planetary protection was a level 1 requirement. We need to ensure that we do not bring any viable terrestrial organisms to Europa. And in case of an anomalous event, that could transport to the ocean, which of course we're trying to study and we feel could host microbial life perhaps. So this analysis was very critical. We had to do everything from an impact model, looking at our trajectory and how likely we might be to impact the Europa body, whether due to a micrometeoroid, whether due to other failures. We had a resurfacing model that, given an impact, looked at the phenomenology of of the geological surface of Europa and how we actually impacted. So this involved a lot of CFD analysis, understanding how we would impact, how we would break up. And then given that we did hit the surface, was anything alive? So did we bring anything with us, and did it withstand that travel from Earth to Europa? And in order to launch, we had to show that this probability of anything surviving this journey was less than 10 to the minus 4. So this whole probabilistic infrastructure actually showed that we met the requirement, but also allowed us to do a lot of different trades on our trajectory, on how on our reliability of the mission, how we flew the mission. So it was really revealing, and it ultimately ended up showing that we didn't need to do a lot of the bioburden reduction and cleaning measures pre-launch. And that saved about $50 million on the project. So big savings there. So that gives you a few examples of how we've been using UQ in systems engineering and how it's yielded and shown several opportunities dollar-wise and technical resource-wise, helped us inform our mission design. And it's proven invaluable. So a minimal investment in UQ techniques has really paid off, especially for missions like Europa Clipper. So now I want to move on to the large language model story. This is a newer technology, of course, to all of us, and we're starting to figure out how to implement that in systems engineering. We've looked at a lot of use cases. I'm throwing a few out here. We've built prototypes for, I think these are polygons, yeah, or hexagons, that for the hexagons in red. I'll talk about the requirements story and how we've applied large language models to requirements development, requirements classification, requirements reasoning, and things like that. We've also done a lot with document analysis, document development, and employing LLMs in that regard. So I'll walk through those examples. So in systems engineering, if any of you are systems engineers, we create a lot of documentation. And so a lot of that is currently in our favorite Microsoft Office suite, sitting in a SharePoint site or on our personal computers or a repo somewhere. And we're trying to get that off of everyone's laptop or repo, have an LLM read these documents, get this information into a database so that we can query it, so that we can start to learn from our past performance and do better. And ultimately, the goal is, can we ensure a digital end-to-end enterprise that enables a digital twin? That's kind of our end goal with this LLM infrastructure. So the first example I'll walk through here is what we call our document analyzer tool. So we use JPL, large language model. It's behind our firewall in our cloud, to provide a repeatable and scalable solution to converting our PDF documents or Word documents into what we call triples, subject, object, predicate form, and putting them into a knowledge base so that we can query them. We started with a few JPL rules or NASA NPR documents. These are policy documents. We started seeing if the LLMs could read those. Those are all public documents. And we tried to see what they could do. A lot of unique challenges popped up, everything from how we chunk the documents, get them into the LLM. There's a lot of strategy in that, to how we handle tables versus figures versus text. So there was a lot for us to learn there. We came up with kind of a 4-step process, and starting with the pre-processing. We've got to get these PDF documents into a markdown form. We chose to use HTML. It was really easy to start removing tags in that format. We needed to chunk, again, these documents into meaningful partitions. That's what chunking means if you're not familiar with that term. So you have a 1,000-page document, for example. You can't, due to token limits, you can't typically throw that whole document at the LLM. You need to think about how to break it down meaningfully so that you can later query that content. The second step is characterization. So we needed to have an interface where we can to help us break up these chunks and partition them appropriately. We chose to, in step 3, generate an ontology from these documents. And this is perhaps an optional step as LLMs get better and better all the time. But the ontology generation ensured a guardrail. So it helped limit hallucinations in the LLM. And basically what that did was, through the LLM prompting, we told the LLM, hey, generate ontology for this document, which is just a vocabulary that you're going to adhere to, and use that as I query it. To check our ontology, we used GraphDB, so some visualization of how these ontologies all fit together and related to one another. And we did that as kind of a quality control measure. So this is, once we had that infrastructure in place, we were able to do a lot of things. This shows, you have a NASA NPR document, you tell the LLM to extract the shall statements, you get something like this on the right-hand side. In systems engineering, we either use DoorsNG or JAMA to manage our requirements. So we quickly, through the JAMA API, pulled those shall statements in like we would any other mission requirement. And we were able to edit those requirements in JAMA and work with those alongside our other project requirements. Then we wanted to use those requirements, which are policy requirements, to assess project compliance. So we had an old Mars 2020 environmental impact statement. And so given that impact statement balanced against the NASA NPR, can we ask the LLM to categorize the Mars 2020 MMRTG in terms of nuclear classification? So we specifically asked it, does the Mars 2020 MMRTG, which is our power source, nuclear power source, does it comply with a tier 2 nuclear safety classification? And so we followed the process I showed before. This table in the upper left is the tiering criteria out of the NASA NPR. We turn that into ontologies. It looks like this bottom left. And then we ask the LLM, again, what tier is this? And you'll see my human assessment as a non-nuclear expert here in the middle. And you'll see the machine's assessment here on the right. And it's pretty good. In fact, so each of these metrics on the left-hand side, it made the correct classification on the machine side. The interesting thing was that the machine, because it was reading the text so literally, it actually found some ambiguity in the NPR policy that the NASA side didn't know was there in terms of the type of fuel being used. So it classified Mars 2020 MMRTG as tier 3. It was actually a tier 2, but again, it revealed ambiguity in the language that the mission actually could have, should have, if it were taken literally, been classified as a tier 3. So the LLM ultimately got it more correct than the human. So that's kind of the document analysis side of things. Just really quickly to go through the requirements development. Traditionally, we develop level 1 requirements. They're given by the customer. We have teams and working groups developing level 2, level 3 requirements. And, the goal here was, can an LLM help us? Can it help us generate requirements? Can it help us assign properties? Can it check for missing requirements? Things like that. So we trained it on a couple requirement sets. We have 2 missions, SphereX and NeoSurveyor. We fine-tuned things a bit, and we asked it to develop requirements for a new mission. The goal was to develop a standard requirements library and by learning from other missions. And so the basic result was, yes, it can do that. As you got to lower levels, level 4 and below, it didn't do as well. But we were able to generate some template requirements for a new astrophysics mission, for example, by training it on some of our past missions. Some other things we did were requirements categorization. So often you categorize a requirement by key and driving. Key meaning, could it result in mission failure if it's not met? Driving meaning it might drive budget and schedule. The LLM was able to read these requirements and do this pretty well, again, having been trained on past data sets. Similarly for V&V method, it was able to recommend a V&V method for that requirement, whether it's inspection, test, or otherwise. It did pretty good, about 85% successful when we deployed it on our test withheld set. I won't go through exactly how this is done, but we used text embedding and then some traditional machine learning methods like sport vector machines to do this. Another thing we looked at was parent-child identification. Can we recommend parent-child relationships? Did pretty well at that. Due to our imbalanced data set, it didn't do as well as we liked. And then quality checks. So we deploy the LLM on a requirement, and we also give it some additional documents like a project dictionary, and we say, does this requirement make sense? Is there anything ambiguous about it? Do we need to fix anything? Did very well in that use case. I think I'm nearing the end of my time, so I'll skip through this, but it's also really good at translating requirements into other, quote, languages. So if you have a tool that will reason over requirements like SysML, FRET, like I'm showing, it will do a good job translating that requirement into the right format. In summary, we're continuing to build out the systems engineering AI lab and adding various LLM modules to help us do our job more efficiently. Yeah, so I'll pause there for any questions. I know I went a little long.
So if we have any questions in the room, go ahead to the mic and ask your question. We have someone coming to the mic. I thought we did. Just one second.
Hi. Yeah, thanks so much for coming here or coming to chat with us. I'm wondering if you have a more complete write-up of your LLM application. I'd love to read a little more.
At this point, it's still in PowerPoint form, but I'm happy to share that with you. We're actively writing a paper, but I'm happy to share the PowerPoint.
All right, thank you.
Yeah.
Any other questions for Kelli? I'll ask you this question real quick, Kelli. So at the beginning of each talk, you talked about using uncertainty quantification to understand the risks in designing systems. And, you know, to be able to do that, you need some information to start off with, whether it's empirical or it's based on subject matter expertise. In general, in your experience, what do you end up having to rely on most heavily to determine what your probability distribution will be?
Yeah, good question. That is definitely the hardest part. It's really problem dependent. In the science model I was talking about that we were injecting faults due to radiation, we relied on historical mission telemetry for that. How often do our missions go into safe mode due to SEUs, things like that? So we have a a data set. It's not necessarily specific to our mission. It's in the rough environment our mission will fly, but in that case, we use that. In other cases, like planetary protection, where we were looking at the Europa geological surface, there's not much there. We had to rely on a lot of models from scientists and other things like that to get our data set. So it really is problem dependent. Like you said, can be subject matter expert derived, data derived, or even simulated data that we use.
Thank you, Kelli.